So today I want to present you our work on a new method. We call it cyclic immunofluorescence. It's a highly multiplexed high content image platform that you can use to probing both liquid sample and the tissue section. So let me try to quickly go through the general method that we are using for the cyclic immunofluorescence. So the goal of the cyclic immunofluorescence is try to extend your capacity to do compared to the traditional immunofluorescence. That's typically limited by the spectrum. So you can do like 4 or 5 different antibody at once. That's at most. But by using a repeated standing and descending method, we can now expand our capacity to up to 30 different antibody at once. That's on a tissue sample. So let me quickly go through our method like cyclic immunofluorescence. So as you can see in the method here, the basic concept is really easy. So if you do whatever you're standing first, like you do for the traditional immunofluorescence, then we use the chemistry method that we can just delete, or you say bleach the fluorophore. Then you can do it again and again, and by repeat this method, now you can achieve like multiplex image in the same sample. So like in here, a simple case, if you can show right here in the method part, it's that we have first thing that is the full color that we do for the nucleus stand. Then you do this, we call the fluoro bleach inactivation method. Now you can stand for 4 different antibody in the same cell that you can see that now you change to a cytoplasmic stand, although you probably cannot see detail like what antibody are we using. But the concept we can use for the both in the cultural cell, like in here you can see individual cell that's done in 96 well plate, and also we can adapt the same method to the slide. So that allow you to do with the tissue sample or clinical sample. And the same concept can apply for all type of tissue or all type of sample. And here, so on the top, our result, our first result, you can see right here. So let me try to go through more detail. So if you can see right here, this corner, so we have performed we call the cyclic immunofluorescence or CyCID. That's in a 96 well plate, and we done like 10 cycles of CyCID that allow you to probe at the same time like 30 different antibody. That gives you very first thing is very enriched data that you can do a bunch of the single cell analysis that people cannot do before, or you can only achieve with other very expensive instrument like cyto or something else. So, and also these things can go not just for the quantitative study like we here to show just 10x image, but we can also do something like even more high resolution. For here, we show it's like high content image we done in a confocal microscope. Then that's the things you can do 60x image. Now you just look at one single cell and you can probe like all different subcellular localization protein as well as some sort of phosphorus signal at once. So that's kind of our advantage to use this highly multiplex image platform. Okay, so now we shift gear a little bit. Like we can also use the same thing with a little help from a company called RealSight. We now can use the same kind of concept and doing with the liquid biopsy. In here, we demonstrate it's a human blood. Then we can actually try to find a circulating tumor cell in the blood sample, as well as not just identify the cell, but also at the same time try to probe all different kinds of markers that associate with tumor progression. So a same concept that we can use for not just clinical sample, but also more research setup. So in the next things, we show that we can try to dissociate a mouse brain and make single cells spread on the slide using the same technology that we are using for the human blood. Then we can probe for, like in here, we do a 4 round of staining, or already give you 12 different markers. Now you can do a clustering analysis as well as high dimensional representation in 2 dimensions. That's this plot you can see here to identify the specific subpopulation. The most interesting idea here is now you can treat this as we call it image cytometry method, but at the same time you can use the concept, the sense of antibody, try to do it in situ. So here is it's one undissociate the mouse screen. So you use the same type of antibody and try to probe it again, and you can try to extract the single cell data from this intact tissue. Now you not only have the single cell data, but also have the rich spatial information. For example, you can see a kind of clear here, you have some sort of cluster of the signal together. Now you can see what kind of different cluster in different region. So, and also then we quickly move from the more research setup to more clinical setup. Now we can probe the sensing on the tumor sample. Here we call it digital and multiplex histology. Now you can see this kind of beautiful picture. Sorry, I don't have time to go over it in detail, but now you can use your imagination and also your available antibody to do a whole bunch of combination in the same tissue. And in the end, will be very interesting to see. So now if we just run in for one particular case, here is a pancreatic cancer cell, and now you can actually extract each single cell data and do this we call the digital representation, as you can see in the, right here. So you can clearly see it's captured almost 100% of the image shown here. But not only that, you can actually extract all the single cell data and try to do the dimension reduction we showed before that in image cytometry setup, and as well as try to see all kind of signaling correlation in this kind of the spatial resolution. So in the end, we just want to prove a concept that all this kind of method can be applied for different type of tissue. So we use the tissue microarray that contains 30 different tissue, and also for each tissue have 2 like tumor associated with that particular tissue. And we run through like 8 rounds of staining and get 24 different antibody staining. And now you can first see like you can do a bunch of very cool stuff with this thing. But first thing we just want to demonstrate, it's actually very clearly distinguished from tissue to tissue. You can see like each color represents one tissue, and after dimension reduction to plot into 2 dimensions, you can now see the individual island of different tissue. And also you can kind of see, so in the middle part here, you can see like red part is the tumor sample, and the blue part is the normal tissue. Now you start to have the ability to distinguish the tumor and the normal tissue using this kind of technology. And also you can go through like just one tumor type. In here we go through like just pancreatic cancer in different stage. Now the things we found is in the early stage of pancreatic cancer, you can see they are more close to the their original origin normal tissue. That's the pancreatic tissue. But if in the late stage you start to see this kind of fuzzy phenotype that we call the heterogeneity of this tumor. So now it's not just far away from their original tissue, and also they are also more diverse from themselves. So in the end, I just want to say this still is a very like new technology. We are still trying to develop it and optimize. Feel free to email us if you have any question. And I want to all the collaborator and also my advisor, Peter Soger. And also thanks for the chance to present in this wonderful conference. Thank you so much.